Hello, and welcome to my channel. This is an educational channel where we try to look at uh, obscure and um, esoteric theories of everything, things that you can use to sort out your whole life and to be able to see things in a holistic manner. And today is the 320th video that we've done on the reciprocal system of theory. And the reciprocal system was originated by Dewey B. Larson. And Mr. Larson worked it out over 60 years of his life. A lot of it solo. He had a small following, in the last 20 years or so. He died back in 1990. And, he started out looking for solutions to much smaller problems. But then he eventually had a few epiphanies, and he realized that he had stumbled upon something that was much bigger. And he answered the call, and he worked it out. And he made some great findings that I'm trying to share with you here. As far as I know, this is about the only channel that talks about this in any type of detail. And it is a difficult thing. You have to put some dedication into learning it. But you had to do this for your high school chemistry class, your high school physics class. If you put in that kind of an effort, you do class every day for half an hour, 45 minutes or whatever, you can make good progress on the reciprocal system. The basic idea behind the reciprocal system is that we live in a universe of motion. This was actually the name of one of Larson's books, Universe of Motion. And this basically saying the universe is composed entirely of motion. Not matter and not energy, but motion. And motion, for Larson, was the relationship between space and time. Space and time, thereby, are reciprocals of one another, and they do not have an independent existence. They are only existent together in motion. Motion is basically a fraction or a ratio with time or space as the numerator and space or time as the denominator. And motion comes in very many different varieties, depending on the coordinates of those time-space factors. And in his first postulate, he articulates some of the constraints there. Time and space both have their coordinate aspects, meaning that they come in 3 dimensions, X, Y, Z coordinates, or Euclidean geometry. So we're accustomed to that idea as far as space is concerned. We tend to see space in X, Y, Z coordinates. But the same is also true of time. Even though those two are distinct, X, Y, Z coordinates in space are they're not the same as the coordinates of time. They're analogous, but not the same. And then you also have what Larson calls clock time and clock space. This is a scalar motion that is progressing. So you can think of this in the familiar term with time, clock time. The clock is always getting later and later and later. And that is what Larson calls a scalar motion, a motion that has a magnitude, but it has no specific direction. The clock is getting later, but in no specific direction. And then in terms of time, clock time means that everything is getting farther and farther and farther apart. And um, that is envisioned using a balloon with dots on it. If you blow up the balloon, all the dots are moving away from each other. But they're not moving in any specific direction. So that is like the clock space, or the progression or flow of space. And in addition, time and space both are quantized, meaning that they have a minimum unit. There is a minimum unit of time and a minimum unit of space. If you don't have that full unit, then you don't have either one of those things. This is relevant also for forming two other regions of the universe. Now, basically, this part of the postulate really divides the universe into 4 parts. Because if you have exactly 1 unit of space in 1 unit of time, now just think space over time, space divided by time. Keep in mind that motion is a fraction with time or space as the numerator, space or time as the denominator. Okay, so there's many different kinds of motion, and each one of them has kind of a different time-space setup. And the most basic kind of motion that we know of is speed. Speed is space over time. The bicycle is moving 15 miles per hour, 15 miles of space in 1 hour of time. And so if you have 1 unit of space in 1 unit of time, you have a speed. And it's what Larson calls unit speed. 1 over 1 equals 1. But this unit speed turns out to be the speed of light. So in Larson's system, the speed of light is unit speed. And the speed of light is also really like the origin, or the ether, the reference point, the 0 point, the null point, this state of rest of a universe of motion is motion outward in all directions at the speed of light. Which contradicts Einstein, who says that the speed of light is the maximum speed of the universe. Larson is saying that the speed of light is the midpoint of the universe, and that an entire half of the universe is moving faster than the speed of light. And then half of the universe is moving slower than the speed of light. So that's the first division. That divides the universe into 2 halves. The half that's moving faster than the speed of light is called the cosmic sector, and the half that's moving slower than the speed of light is called the material sector. And then within the cosmic sector and within the material sector, you have another division, or really another 2 divisions, that divide each one of those halves into 2 regions. So you end up with 4 separate regions. And this is the quantum boundary. So within the material sector, you have what is called the time region. And the time region occurs in places where you're talking about less than 1 unit of space. So when an interaction is occurring within 1 unit of space, remember, if you don't have space, if you don't have a full unit of space, then you don't have space, because you have to have a full discrete unit before you have it. So if you don't have space, then you only have time, because the universe is made out of space and time. It's the contents of the universe. So it's got to be one or the other, or both. And so if you don't have space, you only have time. So that is what Larson calls the unit space boundary. Once you cross the unit space boundary, you move into this realm of time only. And Larson refers to that as the time region. So this is really like the microscopic world. The unit of space is 4.56 times 10 to the minus 8 meters, which is, 1/20 millionth of a meter. And so that is, microscopic. Compared to the size of an atom, it is large. But compared to the, our ability to see it with the naked eye, it's way smaller than that. And so when you are in this small region of less than 1 unit of space, you're dealing only with time. And so that is, and when you cross these boundaries, the rules invert. And so when you move into this time region, you're dealing with a different set of rules. And the same is true in the cosmic sector if you're talking about being within 1 unit of time. Now, the unit of time is 1.52 times 10 to the minus 16 seconds. So if you're talking about an amount of time less than that, you are in what Larson calls the space region. Because if you don't have a full unit of time, then you don't have time. And if you don't have time, then you only have space. And so this is the realm of cosmic atoms and cosmic molecules, the microscopic in time. And the legacy scientists would call that antimatter. Larson calls it cosmic matter. So those are the 4 regions then. So you have the material sector and you have the cosmic sector. And then within the material sector, you have the time region across the unit space boundary. And within the cosmic sector, you have the space region, which is within the unit time boundary. And then, you have the unit speed boundary, which lies between the material sector and the cosmic sector. And if you cross that unit speed boundary, again, the rules invert, which means that you can extrapolate. If you understand the material sector, but you don't know anything about the cosmic sector, you can figure out what's in the material sector because it's the same, or what's in the cosmic sector because it's the same as what's in the material sector, except that you have to invert the roles of space and time. So in the material sector, you have 3 dimensions of space, coordinate space, and you have progressing time, clock time. While in the cosmic sector then, by extrapolation, you have coordinate time, 3 dimensions of time, and clock space, progressing space. So that's kind of how the first postulate works, and that's kind of how the reciprocal system works. That's kind of like the general map. And then Larson kind of took those, and the second postulate basically says that the universe conforms to the rules of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So that is, less important, but it's just basically setting up the math and geometry of the universe, which some of Larson's followers have disputed also. So we'll just, stick mainly with the first postulate. But Larson basically took those postulates and then he did a process of deduction. If this, then that. Well, if this is true, then this would be true. And then if this is true, then this would be true. And he went through 165 steps of deduction to come up with his theoretical universe about, well, if my postulates are correct, this is the kind of the universe that would result. And then he really compared that universe with the universe that had been observed and measured by the legacy scientists. And in probably 90% of the things that the scientists have observed and measured, Larson also came up with theoretically. And then the other 10% generally has to do with what the scientists call the relativistic, the very small, the very large, the very fast, and even the very slow. These are, where Einstein resorts to all kinds of contrivances to explain, like curved space and, where the clock, the Lorentz contractions, where the clock is moving slower, so you end up with things like the twin paradox, where if you're moving at the speed of light, the clock moves slower than if you're not moving at all. And Einstein generally came up with the math for these things, but he didn't have the concepts of why the math works that way. And Larson talks about that quite a bit in some of his works, how the quantum mechanists and the relativists in the world of physics and so on, they have the math, but they don't know why the math works, or they don't have the concepts behind the math. And in some cases, such as Heisenberg, they don't even think that there are any concepts backing it up. They don't think that they have any meaning, that they just are. But Larson provides the why and the wherefore for these things. The reason why we use the Lorentz contractions, the reason why we need to use, so-called curved space is because of this and this and this. So now what we're doing today is we're finishing up this article that Larson wrote on the interregional ratio. And the interregional ratio is basically, I divided the universe up into these 4 parts. When you cross from one region to another, especially when you cross from the macro material sector, which Larson calls the time-space region, to the time region, or when you cross from the time-space region to the space-time region, which is the macro-cosmic sector, with your measurements, when you're measuring across one of these boundaries, you have to compensate by taking into account that you're only seeing part of the picture. You're not able to see everything the way it is, because, again, with scalar motion that has a magnitude that has no direction or no specific direction, it requires 3 dimensions of space to describe 1 dimension of scalar motion. And we have 3 dimensions of scalar motion. So there are 2 dimensions of scalar motion that are not able to be represented by a reference system, by a coordinate reference system. And so we have to take that into account. And so there is a certain amount of kind of compensation that you need to factor in about what you're not seeing. So if you're seeing something, you're only seeing a certain fraction, certain percentage of what's actually happening. So you have to turn around and multiply that to get the real measurement of things. And so this is a crucial measurement that's made, the interregional ratio, which helps you to determine, for example, the basic properties of matter, the interatomic distance, the compressibility. You need to use this interregional ratio in myriad different circumstances when you're trying to do science with the reciprocal system. Okay, now I did the first half of this paper yesterday, so if you want to start at the beginning, you want to go back that far to yesterday's video. So I'm going to start here right in the middle of this paper. Any two scalar magnitudes of the same kind can be added algebraically. Thus, 2 gallons of water plus 3 gallons of water amounts to 5 gallons of water. Scalar speeds are additive in a similar manner. A speed of x units added to a speed of y units arrives at a total speed of x plus y units. But if the second of these motions is taking place in 2 scalar dimensions, with speeds of y and z respectively, the quantities y and z are independent by definition. Since z is independent of y, it is also independent of x plus y. It follows that when a motion is taking place in 2 or more scalar dimensions, only the speed in one of these dimensions can be added to another speed. Again, you have to keep in mind that it requires the entire reference system, 3 dimensions of space, to describe 1 dimension of scalar motion. So if you have 2 dimensions of motion, then you're not able to represent that in a reference system. So, so he says, when a motion is taking place in 2 or more scalar dimensions, only the speed in one of these dimensions can be added to another speed. The same principle applies where there are other differences between scalar quantities. For example, that between motion in space and motion in time. That's what you would get if you crossed that unit speed boundary from the material sector to the cosmic sector. You go from motion in space to motion in time. You would do the same thing if you crossed from the macro material sector into the time region. You cross from motion in space to motion in time. Motion in the time region is an extension of ordinary vectorial motion into a second speed unit, a unit of motion in time, which, for reasons explained in my books, acts as a modifier of the spatial speed. That is, as motion in equivalent space, rather than a motion in actual time. As one of Larson's followers, Dr. Bruce Perret, would say, we don't see time, we only see space. And so when a phenomena occurs in time, we see it as its inverse quantity in space. So that's kind of like a white dwarf star. A white dwarf star is a star that is exploding, but the explosion goes beyond the speed of light. When the explosion is so powerful that it goes beyond the speed of light, that means that instead of exploding into space, it starts to explode into time. And when something explodes into time, we see it as an implosion in space. And so the star implodes in space and it becomes super small and super dense, like a white dwarf star. So that's an example of what we're talking about here. So it becomes a modifier of the spatial speed. That is, as motion in equivalent space, it's rather than a motion in actual time. The real motion is occurring in actual time, but we see it in equivalent space as the reciprocal of what is the phenomena really is in time. So if it's exploding in time, we see it as imploding in space. As long as the net total motion is below the neutral level, there are no fractional units in the universe of motion, but the equivalent of a fractional unit of space or time can be produced by adding units of the inverse quantity. or the inverse entity. A speed in the range between 1 unit of motion in space and 1 unit of motion in time, which is 2 units when measured from the spatial 0, can be obtained either by adding a fractional increment to a unit of motion in space or by adding a negative fractional increment to a unit of motion in time. Like scalar motion in different dimensions, scalar motion in time is independent of scalar motion in space. And these two different procedures therefore produce results that are independent. The full range of the time region motion is 2 scalar units, from 0 spatial speed to 0 temporal speed. Inasmuch as the motion beyond the unit speed level is independent of that in the range below unity, it is not limited to the one dimension of motion represented in the reference system, but extends over all 3 dimensions. In each dimension, the speed may be either a modified spatial unit or a modified temporal unit, as indicated in the preceding paragraph. Consequently, there are 2 to the third, or 8, different permutations of the spatial and temporal motions. Of these, only one, the all-spatial combination, SSS, is commensurable with quantities in the reference system and appears as a magnitude in that system. If one of the spatial motions is replaced by a temporal motion, as in space-space-time, the resulting combination of scalar quantities is different from space-space-space and independent of it, just as the dimensional combination x plus z is independent of the combination x plus y. The same is true of the other possible permutations. The complete list is SSS, SST, STS, STT, TSS, TST, TTS, and TTT. Those are the 8 possibilities, or eigenstates. Here, then, is the size of the container, the capacity of the single space unit to contain compound units of motion in which the introduction of time components produces the equivalent of less than a unit of space. What we want to do next is to determine how many units of motion in the form of matter can exist in this 8-unit container. We have seen that the rotational motion of the atom around one of its 3 axes is one-dimensional. Each such rotation constitutes 1 unit of motion, and since the container has room for 8 units, it can accommodate 8 of these rotations. So far as we have been dealing with dimensions of space or time, equivalent space, now we need to take into account the fact that the atomic rotation is taking place in 3 dimensions of motion, each of which can be resolved into 3 dimensions of space or time. In the 2 additional dimensions of motion, the rotation of the atom is 2-dimensional. Okay, well, I was hoping to get done with this paper here today. I guess it's not. There's not much more here. Okay. Each unit of this rotation occupies 2 of the scalar units of the container. Thus, only 4 such rotations can be accommodated in each dimension of motion. The total number of different combinations of rotations for the motion as a whole is then 8 times 4 times 4 equals 128. What this means is that the space unit can contain 128 independent scalar motions, only one of which is the SSS combination in the one dimension of motion represented by the reference system, appears as an observable quantity in that reference system. For the rotational motion alone, the ratio of total to observable rotation is 128 to 1. So when you're just dealing with rotational motion alone, the interregional ratio is 128. But that can be complicated if you're dealing with also with other kinds of rotation, other kinds of motion, such as vibrational motion. The fact that the rotational motion is a rotation of a vibration introduces an additional factor, as the units of motion involved in the vibration add to the total motion content of the atom. As explained in my book, this addition amounts to 2/9 of the rotational motion, making the complete interregional ratio 1 plus 2/9 of the rotational motion, making the complete interregional ratio 1 plus 2/9 times 128 to 1, which turns out to be 1408 over 9, which is 156.44. Now, if you are dealing with only a subatomic particle, then you only add 1/9 instead of 2/9, and you end up with the number 142.22. So you deal with different interregional ratios depending on what kind of motion you're dealing with. Just the photon is 128. An atom is 156.44, and a subatom is 142.22. Okay, go over this very slowly if you want to really get it. And thanks for tuning in today, and have a great night.